my previous video, I had discussed about orthogonal vectors, orthogonal complements of vector, and when a subspace be orthogonal and when a basis are mutually orthogonal. I had seen in my previous video this is. Today I will discuss these topics also elaborately, because this topic I have told you this is very important for competitive exam, and not only competitive exam, for higher study also. At first, just recall the orthogonal complement. Orthogonal complements of a vector. Consider W be subspace of Rk. Then W perf is the collection of all those vectors in Rk, which are actually orthogonal to all vectors in W. W perf contain set of those vectors in Rk such that inner product x with W equal to 0 for all W belongs to the subspace capital W. We all of us know this is. Now consider U1, U2, UD is a basis vector of W. Then x belongs to W plus imply x is orthogonal to all vector in W, and x is orthogonal to all vector in W imply obviously x is orthogonal to this basis vector. That means since U1, U2, UD be the basis vector of W, so inner product x with Uj equal to 0 for j equal to 1 to up to d. That means there exists a conclusion. X belongs to W perf means x is orthogonal to all basis vector in BW. Are you getting this conclusion? Well, conversely, consider x in Rk is such that x is orthogonal to all vectors in BW. That means x is orthogonal to all basis vector. That means obviously inner product x with Uj equal to 0 for j equal to 1 to d. Now take any arbitrary vector small w belongs to capital W. Then obviously since all Uj be the basis vector, so W can be expressed linear combination of this basis vector for W. That means small w equal to alpha 1 U1 plus alpha 2 U2 up to alpha d UD. Then inner product x with W would be such type. Then omit the scalar. Then this would be alpha 1 times inner product x with U1 plus alpha 2 times x with U2 up to alpha d times x with UD. And x is orthogonal to all basis vector, so obviously inner product x with Uj equal to 0 for j equal to 1 to d. That means obviously this value equal to all this value equal to 0. That means x with W, inner product x with W equal to 0. That means from this expression we can tell x is orthogonal to W for every W belongs to capital W. And since x is orthogonal to W for every W belongs to capital W, that means x belongs to W perf. Conversely, we can tell if x is orthogonal to any basis vector, that means x is obviously belongs to W perf. As for example, consider the set W equal to R4 and small w which is subspace which contain those vectors AB, A plus B, A minus B, where A comma B belongs to R. Obviously this is small w is a subspace of R4. Now we have to find the W perf. It is easy to see the basis vector is of this subspace. Obviously the basis vector of this subspace would be, we all of us know, this contain u1 and u2, where u1 be the 1 0 1 1 and u2 be the 0 1 1 minus 1. Obviously this is the basis vector of small w. That means obviously dimension of this subspace be 2. Now we have to find, actual question is we have to find the orthogonal complement of w. Consider x belongs to w part. That means obviously, since I have seen few minutes ago, any vector belongs to w part means x is obviously orthogonal to all basis vector of this subspace. And since this is the basis vector of w, that means inner product x with u1 and inner product x with u2 obviously equal to 0. And notice this is the u1 and this is u2. Therefore, inner product x with u1 means x1 plus x3 plus x4 equal to 0. And inner product x with u2 equal to 0 means x2 plus x3 minus x4 equal to 0. This is here two equation. Consider x3 equal to alpha and x4 equal to beta. Therefore, x is of the form minus alpha plus beta, minus beta, minus alpha plus beta, alpha beta. Obviously alpha beta belongs to R. That means obviously W part contain such type of set. Okay. And that means the basis vector of W part would be minus 1, 1, 0 and minus 1, plus 1, 0, 1. Are you getting? This is the basis vector of W part. And notice one thing. BW contain these two vectors. So dimension of BW equal to 2. Similarly, BW part contain these two vectors. So dimension of BW part is equal to 2. That means dimension of W plus dimension of W part is actually equal to 2 plus 2 equal to 4, which is similar to the whole space R4. Therefore, the basis vector which contain 1, 0, 1, 1 and 0, 1, 1 minus 1 also. What is the basis vector of W part? This is actually minus 1, 1, 0, minus 1, 1, 0, 1. Notice these vector, this is u1 and u2, this is v1 and v2. These vectors are linearly independent and these vectors span whole space R4. That means this is actually the basis vector of R4. Are you getting the idea? Oh. Therefore, I have got to idea dimension of W plus dimension of W part equal to whole R4 and basis of W union basis of W part equal to the basis of R4. So, actually dimension of W plus dimension of orthogonal complement of W part is actually similar to whole RK. Therefore, this is actually very interesting matter. If you have any subspace W in RK, then dimension of W and dimension of orthogonal complement of W part, this union, this addition is actually the whole space R of RK. Therefore, every x in Rn can be written as a sum of vectors xw of W and a vector xw part of W part, where W be any subspace of Rk. That means the xw is called the orthogonal projection of x onto the W, and xw part is called orthogonal projection of x onto W part. And this is actually the new idea. What is the orthogonal projection? Just look the picture. We all of us know, passing any line who is passing through origin, obviously this is subspace, and consider this is as a vector x, then just project it on this line, on this subspace W, then this is xw and this line be xw part. Okay, that means the vector x can be written as xw plus xw part. Are you getting the geometry? Oh well. Therefore, there exists one theorem. Let V be an inner product space and W be a finite dimensional subspace of the vector space V, and let fix x belongs to the vector space V, then there exists unique, obviously this is very important, unique U in W. Now define a mapping E from V to V such that E of x equal to U, where U is a best approximation to x from W, and this is called actually the projection map of the vector V on the subspace W. In other words, for every x there exists always unique U. Okay? Are you getting what is actually the projection map? Oh, yes. And the general formula to find projection of a vector space to a subspace is, consider V be an inner product space and small v be the vector space, arbitrary vector space, and W be considered as a subspace. Then the projection V on the subspace W is the vector in W which is denoted as projection of the V onto the subspace W. And the rules is such type. At first, find the orthonormal basis V1, V2 up to Vn for the subspace W. Then projection of the vector W on the subspace W equal to, actually rules is summation I equal to 1 to n inner product V with Vi times Vi. First see, here given V1, V2, Vn be the orthonormal basis for W, and for orthonormal basis inner product W is W over norm of W. Therefore, the projection of V on the subspace W is actually by these rules, since this Vi be the orthonormal basis, if I consider the orthonormal basis as an inner product W, then this would be actually notice they had V comma inner product V comma W over norm W with W over norm W, because here Vi also orthonormal basis. Then this is actually inner product V with W over norm W square times W. Then actually this is the formula. Okay, let's say by an example. As for example, consider W be two-dimensional subspace of R3 which is spanned by two orthogonal vectors V1 equal to 1 to 1 and V2 equal to 1 minus 1 1. Then what is the projection of the vector minus 2 to on? Here notice the subspace W is spanned by these two vectors 1 to 1 and 1 minus 1 1. Then at first we have to find projection of V onto the V1. Then by the formula, just this is inner product V with V1 over inner product V1 with V1 times V1, and this is equal to actually 2 over 3 times 1 to 1. Then we have to find projection of V onto V2 would be by previous method this would be minus 2 over 3 1 minus 1 1. Then projection of W on the vector V would be projection of V on the vector V1 plus projection of V on the vector V2. Now put the value, then after calculating the value would be 0 to 0. Therefore projection of V onto the subspace W would be 0 to 0. Are you getting? I have got one nice idea. Consider this is the subspace W and this is with the subspace W part on the vector space V. Then any arbitrary vector x on the vector space V can be split as the vector xw and with plus the vector xw part. Okay? Obviously this splitting always unique. Also basis of B can be split into basis of W and basis of W plot. And any orthogonal basis is split by orthogonal W plus orthogonal W plot. Okay. So any orthonormal basis of the vector space can be splitted by orthonormal basis of W and orthonormal basis of W part. That means actually the whole vector space made by these two subspace W and W. One more simple property of orthogonal complement is consider the Rk as a vector space and W be subspace of Rk. Consider dimension of W equal to D. Now consider W part be the orthogonal complement of W. Then dimension of W part is equal to K minus D. And consider X equal to W part. Then obviously W part be subspace, that means X is a subspace. Then dimension of X equal to, obviously since I have considered X equal to W part, then the dimension of X equal to K minus D. Now here I have considered X equal to W part. If we consider X part, that means this is obviously orthogonal complement of the subspace X. And by definition this is actually set up those vectors in Rk such that inner product x with y equal to 0, where for all y belongs to x, where x equal to w part. And clearly x belongs to w always imply x belongs to x part, because every vector of w always orthogonal to x part. That means from this expression we can tell w contain x part. We can tell dimension of x plus dimension of x part equal to dimension of Rk, because all of us know when x be any subspace, then dimension of this subspace plus dimension of orthogonal complement of this subspace is always equal to dimension of Rk. And notice dimension of x equal to actually dimension of w part, and dimension of x part means dimension of w part to the part equal to dimension of Rk. And dimension of w part to the part always equal to w. So by this expression it is true dimension of w part plus dimension of w equal to dimension of Rk. That means I have got dimension of w equal to dimension of w part to the part. And from this expression W contain X part always imply W contain W part to the power part. And since dimension of W and dimension of W part always same, that means actually W equal to W part to the power part. We will see one example. Consider the matrix A and W considered as a row space. Then find the basis of W part. That means actually we have to find those vector which is perpendicular to all vector of row space. And we all of us know this is actually nothing but null space of this matrix. Mathematically, actually W bar is set of those vector x such that x is orthogonal to each row of the A. And this is actually the matrix, that means Ax equal to 0, and this is actually the null space of A. That means the basis vector of null space is actually the W part. Is here pivot only this column. That means this is the free variable. From this expression we can write x1 plus 4x4 equal to 0 and x2 plus x3 plus 6x4 equal to 0. And I have considered x3 equal to s and x4 equal to t. That means x1 equal to minus 40 and x2 equal to minus minus 60. Are you getting? Therefore, x is combination of these two vectors. Therefore, basis vector of W par contain actually these two vectors. That means perpendicular of row space, that means orthogonal complement of row space of A, actually nothing but null space of A. Are you getting? Oh, my all viewers know this part in clearly because I had discussed in my earlier video. We all of us know in my previous video I had seen there exist 4 subspaces. 1. Range space of A transpose and null space of A. These 2 subspaces be from Rn, and other subspace range of A and null space of A transpose, and these 2 subspaces B belongs to in Rn. I had drawn these 4 subspaces in my earlier video. Just see it elaborately. See, if you don't see my earlier video, please see earlier video. And I had seen orthogonal complement of range of A transpose is actually the null space of A, and since complement is actually this space, so if we apply both side complement again, then this would be null space of A part equal to range of A transpose. Other subspace would be the orthogonal complement of range of A would be, we all of us know, I had seen in my earlier video, this is actually the null space of A transpose. And similarly, if we apply in this equation again part, then I will get null space of A transpose part equal to range of A, and this subspace belongs to Rm. Means dimension of W and plus dimension of W part equal to the whole dimension of the vector space. Therefore, dimension of range of A transpose plus dimension of range of A transpose part always equal to n, and dimension of range of A transpose this is, and dimension of range of A transpose equal to actually dimension of null space of A, which is equal to n, and dimension of range of A transpose means actually the rank of A transpose and dimension of orthogonal complement of range of A transpose is actually the null space of A, and dimension of null space is actually the nullity of A. That means rank of A transpose plus nullity of A equal to n. Okay. On the other hand, bi-rank nullity theorem gives rank of A plus nullity of A equal to dimension of B, which is equal to n. Therefore, if you equate these two equations, then I will get obviously rank of A and rank of A transpose always be equal. Are you getting? And this part is very important for any competitive exam. Rank of A and rank of A transpose always same. Now look the picture again. This is Rn and this is Rm. And in Rn, the two subspace are range space of A transpose and null space of A. And these two subspace are always perpendicular to each other. Okay. And this is the orthogonal complement of this space. Similarly, in Rm, these two are subspaces, and these two subspaces are orthogonal to each other, and null space of A transpose be the orthogonal complement of range space of A. That means every vector in Rn can be written as sum of these two space, and if you see the basis vector of range space of n transpose, range space of A transpose, and basis vector of null space of A, this is actually the basis vector of Rn. Okay. Then I will see the orthonormal basis vector of range space of A transpose and orthonormal basis vector of null space of A. This is actually orthonormal basis also, the Rn. Similarly, I will see the basis of range space and basis of null space of A transpose, and these two bases are actually the basis of Rn. And similarly, I will see the orthonormal basis of these two space, and dimension of range space of A transpose is actually the rank, and I had seen rank of A and rank of A transpose always equal, so this is actually same as rank. Similarly, this is range of A is similar to dimension of range of A is rank. This is actually the rank, and dimension of null space of A is actually the nullity of A. That means this is actually the nullity of A, and dimension of null space of A transpose, this is actually the nullity of A transpose. This picture and this topic is actually very important for any competitive exam. Please see this picture with pay attention. I will give in my next lecture some more information about these matrices. Okay? But at first, please pay attention in this topic. Okay? Today I will stop here. See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.